All right, welcome back. We are on chapter 13. We are looking at kinetics. We're looking at the rate of reactions, and this is our fourth video. If you remember back to where we were talking about change of energy of reaction and activation energy. We're going to look at it a little bit more, and let's get going with that. All right, so we are talking about things that affect if a reaction will occur and how fast it will occur. There's a couple things that have to happen for a reaction to take place. First off, the reactant molecules must find each other and they must hit each other and collide. This will get those reactants turning into products. All right, now a lot of times a reaction might require a specific orientation for this reaction to take place. So the reactant molecules has to come in at the right place to the other reactant molecules for them to collide. If they don't, reaction might not take place. Also, another important thing is not only do they have to find each other and collide, but they have to have enough energy. What is this energy needed? Anytime you have to break bonds, and that's what's going to occur in the reactant part, you have to have energy to do that. Now we know that when you form the bonds, you're going to release energy, but you have to at least have enough energy to be able to break the old bonds. All right, so some factors that will affect how fast this will occur. We're going to talk about these in more depth here in a couple seconds, but the temperature is a big one, and you can probably make some sense of that, right? If the temperature is higher, the molecules will have more energy, so they'll be moving around faster, they'll be colliding more frequently. Also, if they have enough energy, it's going to be easier for them to break those old bonds. They'll be over that activation hump a little bit faster. Picture there, you can see glow sticks, all right? That's something that's common. There's a reaction taking place here. And if you want to try this with the glow stick and go to the dollar store, buy yourself a couple glow sticks, put one in some hot water. You can leave one out normal room temperature, and you can put some in some ice water, and you can see really dramatically how the reaction rate is affected. You can see the glow, being more intense for the one that's in the higher temperature water. If you want to save your glow sticks, this is what we have in my freezer at all times with all the children. They often will break their glow stick and want to save it. So in my freezer, I probably have several glow sticks. Now, it's probably been too long, they're probably no good, but the kids think that's a fun thing to keep their glow sticks longer. All right, so besides temperature, concentration is also something that will affect a reaction. The stronger the concentration, the higher the concentration, the faster those reactants will be able to find each other, collide, and so you'll have a faster reaction. Nature of the products is another way that you can also then include, speed up the reaction. We'll talk about that in a little bit as well. And then also a presence of a catalyst. So we'll talk about those things. I know we've brought them up already in these lecture series, but let's look at them a little bit more in depth. First one, temperature. We talked about this a little bit, Temperature is a measure of kinetic energy, how much energy those molecules have, the energy of movement. Higher temperature, the faster they will move, And if they're moving around faster, they're going to find each other, collide more frequently. Higher temperature also then would give enough energy to get over that hump, That hump from where the reactants start to where they have to go to get to that top of that transition state is called the activation energy, So the more energy you have, or the higher the temperature, the more molecules will go over. Now, the temperature change does not affect the activation energy. However, it just gives more molecules enough energy to make it over that hump. All right, so that's temperature effects. Let's move on to a couple other things. So the orientation. Now that we mentioned this already, and I think we've seen this little bit of a reaction. One of the mechanisms might be a substitution reaction. All right, and you can see this one molecule coming in. All right, and we have a methyl bromine here. And you can see that bromine bond has to break away, and we're going to make a new bond, all right, with I think that's a carbon there, oxygen, that has to come in. Now, if it came in from the other side and came in towards the bromine, that collision would not result in an effective reaction because it's not coming in with the right orientation. So it has to come in from the back side here. So we have to start forming a new bond, and the other bond is breaking. So that is one thing. Orientation will affect the reaction. Some reactions have specific orientations that have to come together. Others might not be as specific, so the reaction rate might go faster. All right, effective collisions, this puts together two things. All right, so one, the collisions has to be proper orientation in order for it to be effective. And also, it has to have sufficient number of energy. So if the two molecules collide, but they don't have enough energy to break any bonds, it doesn't matter that they collided because you don't have enough energy to get over that activation energy. All right, so the reaction rate then is the product of the energy and these orientation factors. So you can see this kind of an energy factor here. Okay, that's the number of collisions per unit time that's affected by concentration. And then also, they have to have enough energy to get over that activation energy hump. All right, so that's the energy factor. The orientation factor is the fraction of collisions that have molecules with the proper orientation. So put those together and you will affect the reaction rate. All right, looking at this a little bit more. Let's get this going here. So the top one is what we were just looking at. Reaction rate is equal to that energy factor times the orientation factor. Let's pull apart the energy factor. All right, so the energy factor has two things in it. Number of collisions per time. I'm going to pull to right there. And then the amount of them with the energy equal to or greater than the activation energy, we're going to pull right there. All right, so that will then lead to this. I'm going to put these two together. These are things, okay, the fractions of collisions with energy equal to or greater than the activation energy, and the fraction of collisions which molecules have proper orientation. This is what is required. Those are the two requirements for effective collisions. All right, so that leaves, and these are kind of going to be a constant thing here, at a certain temperature. There will be a constant thing. And then that will leave this right here, which is the number of collisions per unit time. Well, how do we increase the total number of collisions per unit time? And that is by increasing the concentration of reactants. The more concentrated reactants you have, the faster this reaction rate will go. All right, so how do we do that? What are some ways to increase concentration? All right, if you think of concentration, we've been talking about it in terms of molarity. Moles per liter. Well, you can see that we can get the concentration to go up if we increase the number of moles of reactant. So add more moles reactant. We can also increase the concentration if we do something with the volume. What would we have to do with the volume of the reaction vessel here? Since volume is on the bottom here, increasing the concentration by decreasing the volume. All right, and one more thing that we can actually do to increase the concentration is increase the surface area. So what does this mean, to increase the surface area? If you have, let's just say you have some iron, solid iron. If you have maybe 1 gram of solid iron, and you want to have this react, and then you also take that 1 gram of solid iron and get it into little shreds and little pieces, which one would react faster? The one solid gram or the one that's kind of been really small little particles of it? The small particles have more surface area, more area for the reaction to take place, so you therefore increase the concentration pretty much and will increase the rate of that reaction. All right, so we're pulling this out right here, pulling these two together, and let's see what that looks like. All right, here we go. We have now pulled that together, and we can then combine those inherent factors. Okay, those were the two, the fraction of collisions with equal energy, equal or greater than the activation energy, and the number of collisions with the right orientation. We're going to pull those two together. Those are the inherent factors. They won't change as as temperature is constant. Those will also stay constant for the reaction. And we're going to give that the K, a constant. So this constant here is called the rate constant. All right, and a large K will denote that the reaction will go fast. So it's a faster reaction. And if you have a small k, then you have a slower reaction, and that makes sense. So we have our reaction rate is equal to the k, okay, and k is these two factors combined, times the number of collisions per unit time. Now, if k goes up, the rate should go up. And if k goes down, or k is smaller, the rate will be less. So that should make sense. So a higher K leads to a fast reaction. All right, a couple more details about K. We can call it a constant because the activation energy for the reaction does not change. A couple things that would cause that to have a little bit of a change. If you have a catalyst, we'll talk about that in a little bit more detail in the next video, but a catalyst is a new mechanism, so it doesn't follow the same mechanism going from reactants to products as the current one. It's a new mechanism which has, by definition, to be a catalyst, something that speeds up the reaction, it has a lower activation energy. And again, a lower activation energy would mean that you have a larger K, so the reaction should be faster. All right, we'll look at that more. And then increasing temperature will also increase the K because now your average kinetic energy of the molecules has increased as well. All right, I think, let's look one more thing just to kind of sum it all up here. Let's look at this reaction and just make sure we can kind of put it together and answer some questions about it. This reaction is saying if you have a large value for K, can you answer these questions? All right, so remember that K is equal to the number of collisions with energy equal to or greater than the activation energy times the number of collisions which the molecules have the proper orientation. So that's what K is, those two things together. And we can talk about the rate of the reaction is equal to that K times the number of collisions per unit time. All right, so what does the K value, being very large, say about your activation energy? All right, so the activation energy comes in here. And if K is large, that means that the number of collisions with energy equal to or greater than the activation energy must be large. So that would usually indicate then that activation energy is likely small, is not that big of a hump to get over. So if K is large, then the activation energy is most likely small. All right, let's look at the next question here. What does this magnitude say about the orientation requirements? All right, so if K is big, what does that have to say about the orientation requirements? All right, if we're having a fast reaction, that means that the orientation here probably isn't very specific. It's not a large concern for this reaction. Maybe the molecules can hit whatever way they want to. There's not one specific way that the molecules must hit together to go from reactants to products. So a large K then the orientation is not a large concern. Not a very specific reaction on how the mechanism takes place. All right, and then the last question, this one should be pretty good, easy for you. If we have a large K, so K value goes up, what does that mean about the reaction as far as its rate? Is it intrinsically fast or slow? So the larger your K, this should mean reaction is fast. All right, next video we're going to look more at the catalyzed reaction and what that does to the activation energy, but that's it for this one.